Okay, so we've talked about critical numbers before, and we're gonna, be more definitive and truly define them. And we also want to understand how they relate to extrema. Remember, we just talked about extrema in terms of maxes and mins. So let's see. All right, so if f of c is a relative extrema for f, then c is called a critical number of f. Just FYI, that doesn't say off, that's of f. Okay, so critical number. It's really important for us to understand what a critical number is first, and then we'll come back to this theorem. So let's be given that f of c is defined. C, or some input value, some x value, is a critical number if f prime of c equals 0, or f is not differentiable at c. Okay, so let's understand this again. So something that would be a critical number of a function would be where its derivative is 0. And let's think about where a derivative would be 0. Well, at maxes and mins, right? Unless, of course, it is a horizontal line. But then, remember we just said before that everywhere is a max and min. Anyway, or f is not differentiable. And we know several ways where we could have non-differentiability. So right here it says f prime of c does not exist. Okay. So going back to what this theorem says is that if f of c is a relative extrema, then it is a critical number. And that's really hitting on this point here, that in order to be a critical number, its derivative must be 0, which means it is relative extrema. Okay. Now let's take a look here. One thing that I want to remind us is that, saying that f is not differentiable doesn't mean that we can't take a derivative of the function. It just means that at c, its derivative is not defined or does not exist. Okay. Now, as it says here, it says the absolute max and absolute min of f on a to b, the closed interval a to b, occur either at an endpoint of a to b or at a critical number a, b, right? So what it's trying to say here is that, critical numbers are where relative extrema will occur, right? Based off of our definition. But just because we have a critical number doesn't mean a relative extrema will occur there, but a relative extrema can only occur at a critical number. And that's where an absolute extrema can occur, as well as if it's within an open interval. Okay. That got a little bit wordy, but let's understand by examples here. Okay. So we have an example, this graph here. Okay, we're just going to talk about it and kind of visualize what's happening here. Now it does tell us, we do have a relative max, a relative min, and a relative max here. So now you're seeing for really the first time is that, okay, we do have multiple relative extrema. Right, we have two relative maximums. One thing I want to point out here is, yes, this is non-differentiable. There is a sharp turn, and that's why it's non-differentiable. But it's still one of our highest points, but it's not the highest, which is what makes this an absolute max. Here, this is a relative minimum, but it's not the most absolute minimum point. It is over here, right? And just keep in mind here that this is a closed interval, considering the fact that it does stop, right? We do have endpoints, so this is a closed interval. Remember that since it is closed, that this point here and this point, and this point here can't be relative. So like maybe you were tempted at first to say that this point over here is a relative min, but relative maxes and mins can only occur in an open interval. Okay. All right, so absolute max and mins, highest and lowest point on the graph, can be open or closed interval. We just talked about that before. Relative max or min, open interval. Critical values, now this was new, are inputs where the derivative is 0 or does not exist, and they are potential locations of extrema.